Lesson 7.3, Electric Field. We can use a test charge to determine how the surrounding charges generate a force. We're going to pick a small test charge so it doesn't change the surrounding charge orientation. For example, a small test charge, 1 times 10 to the negative 10 coulombs, experiences this force when placed near a charged sphere. Determine the force per coulomb that the charge experiences. All right, so if I want force per coulomb, I should probably take the force and divide it by the coulombs. Which gives me 2 times 10 to the 1, or 20 newtons per coulomb. So if I know that, what would be the force on a 2 coulomb charge? So in other words, if I took the test charge out of the way and I stuck a 2 coulomb charge at that location, I could multiply by my 2 coulombs and get 40 newtons worth of force. So that is the whole point of a test charge, is we could use a little charge and figure out what the charge on something big might be at that location. That way we don't have to work with large charges. This idea of using a test charge to find out about the force in a given area leads to electric field. Electric field is the force per charge. For point charges, that would be kq over r squared, because the force was kqq over r squared, but I've divided by one of the q's. So electric field, so the E is the electric field, force per charge. It's the force per charge. It is a vector, has the same direction as the force on a positive test charge, And if you have multiple things producing our electric field, multiple charges producing electric field, you'd have to add them as vectors. And the unit for electric field is newtons per coulomb. For point charges, our electric field is force per charge. Our force is kqq over r squared. So we'll put that in for our force. But then the q zeros cancel. And so for point charges, the electric field is kq over r squared. Notice the test charge does not affect the electric field. There are 2 point charges. Q1 is 4c and Q2 is 8c. They're 10 meters apart. Find the point where the electric field is 0 between them. So here's Q1, and it is 4 coulombs. Here's Q2, and it is 8 coulombs. And they are 10 meters apart. Somewhere in between is going to be our point where the electric field is 0. So the electric field created by the 8 coulomb charge is going to be larger than the electric field created by the 4 coulomb charge. So the 0 point is going to be closer towards the 4 coulomb charge. I'm going to call this distance d, so this other distance would be 10 minus d. So I'm going to take the electric field from 1 and add the electric field for 2, and I want that to be 0. So since these are point charges, it's kq over r squared. But we do need to worry about direction. So our test charge is positive. So if I had a positive charge there, the 4 coulomb is going to push it away towards the right. So I'll call that one positive. The 8 coulomb charge is going to push it towards the left. So I'll call that one negative since it's going towards the left. Q1 is 4c and its distance is d. Q2 is 8c and its distance is 10 minus d. I think I'll move the right hand term to the other side of the equal sign. Oops. K's will cancel, and I can cross multiply. Maybe I will divide by the 4c. Which gives me 2d squared. And then maybe I'll square root both sides. So it'll be the square root of 2 times d. So if I add a d, I'll have 1 plus the square root of 2 times d, and then divide. So I'll have 10 divided by 1 plus the square root of 2. Which is 4.14. So that means if d is 4.14, the other side is 5.86. So where is it? It is 4.14 meters from Q1. A doorknob, which can be taken to be a spherical metal conductor, acquires a static electric charge of negative 1.5 nanocoulombs. What is the electric field 1 centimeter in front of the doorknob? So this distance here is 1 centimeter. It says the diameter of the doorknob is 5 centimeters, so our radius would be 2.5 centimeters. So the distance, total distance from the center is going to be 3.5 centimeters or 0.035 meters. So our electric field is KQ over R squared. K is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Our charge is negative 1.5. Nano is times 10 to the negative 9 coulombs. And my distance is 0.035 meters squared. This gives negative 1.10 times 10 to the 4 newtons per coulomb. Now, what's the negative mean? The negative means that it was made by a negative charge, but that doesn't really tell us much about the force, since the negative usually indicates direction. So we're going to say our electric field is just the 1.1, so we're going to have our magnitude times 10 to the 4. But we're going to look at our direction. If I have a positive charge here, and the doorknob is negative, it's going to be attracted. So it's going to be attracted towards the doorknob. So our electric field is that, and it's going to be directed toward the doorknob. It would be nice to have some kind of map to show the electric field in space. So here are the rules for making a map. The lines begin at positive charges, and they end at negative charges. The number of lines entering or leaving a charge is proportional to the size of the charge. So if the one charge is twice the size of another charge, it should have twice as many lines. The lines don't cross each other, and they leave a surface at 90 degrees. If the lines are spread out away from each other, then it's weak electric field. If the lines are really close to each other, then it's a strong electric field. The lines can't cross each other because if they did, they would have two different values of an electric field at that point. Each line is going to be a different size of electric field. Here are two different electric fields. The one on the left is the electric field due to a positive point charge. Any positive charge stuck out here would be pushed away, directly away. And the test charge would want to be pushed along the electric field lines. For a negative point charge, it would attract a positive test charge. They would want to follow the electric field lines. So here are positive and negative, so 2-point charges. Any test charge, any positive test charge, will be pushed away from the positive charge towards the negative, and it's going to follow the electric field line. So any positive charge here is going to be thrown away from the positive charge, attracted to the negative charge, and would follow the electric field lines around. If both the charges were the same, they'd be repelled from both, and you can see places where the lines are close to each other, it's a very strong electric field. Between the oppositely charged charges, the lines are close to each other, it's a strong electric field. Between the same charges, when they're both positive, it's a very weak electric field in the center. Here is a really bad electric field map. What are some of the things wrong with it? Well, on the left, our lines should leave at 90 degrees, so they should be kind of curved. You can't cross at point P. And our lines should be proportional. The number of lines should be proportional to the size of the charge. So the two negative Q's should have the same number of charges. The negative 2Q should have twice as many lines going to it. And the 4Q should have twice as many lines leaving it as goes to the negative 2. So let's see about fixing it. Let's have 2 lines per charge. So the negative Q should have 2 lines going to it. Both of the negative Q's should have 2 lines going to it. I'm making them curved so they leave at the surface at 90 degrees. Going to the negative 2Q should then have 4 lines. And the 4Q should have 8 lines. Look at that. It has 8 lines. So that's more of what this map should look like.